And thank you everyone for attending. And well, the subject of webinar is how to evaluate crosstalk in high-speed PCB interconnects. So, as Lucy mentioned, there are a lot of slides, so let's get started. After some introduction, I will talk about a little bit only about anatomy of crosstalk and traces. And then the main subject of this webinar is how actually measure crosstalk, or rather numerically evaluate, maybe measure even, and what metrics to use to quantify it. So, and this webinar is based on the recent tutorial that was at DesignCon 2025, and slides are available. It was 3-hour tutorial, so the only part, 1/3 probably, I will cover today, relevant to the quantification only. So if we consider different effects, different signal degradation factors, so I put them in 4 broad categories here, and absorption is absorption of signal energy in dielectrics and conductors, and there are some application notes at Simberian website explaining how it happens and how to simulate it. Application notes are located in application notes section of Simberian website. Reflections, this account for different types of reflections, from impedance mismatches, from discontinuities, and those two are probably the major reason for signal failure. So, but we will not talk about them today. You can read in application notes again, reference here. So today we will talk about leaks and dispersion, or dissipation, rather into other interconnects. It's a broad subject, usually known as crosstalk. So leaks from some links appear in other links as interference from in form of interference. So in brief, crosstalk is unwanted noise from the coupled structures caused by signal leaks that degrades the useful signal and may reduce the data transmission rate and even cause complete link failure. So crosstalk is usually not the #1 reason for failure, rather number maybe 2 or 3. But it is important nevertheless. Why it is important? Well, first of all, PCB and packaging interconnects are open waveguiding structures. I keep repeating this because of it's not obvious, and I put a few slides and even a little demo of the fields later in this presentation, just to explain what I mean by open waveguiding structure. So it cannot be corrected at the receiver in general. So there are techniques for synchronous signals, how to deal with this. But in general, for serial interconnects, it's not possible. Neglecting crosstalk, well, may cause failure. And we have such designs from our customers and partners that basically failed because of crosstalk, and finding it and fixing was a big deal. Crosstalk is deterministic. It's not just random noise. It's difficult to predict. Why? Because of its uncorrelated noise, so it's bounded. That's important item here. Direct analysis in many cases is costly or inefficient. But the worst case analysis may lead to over-design. Understanding the sources and mitigation of it is very important. So I hope everybody understands this who attended this webinar. So considering crosstalk types, we can separate them in two categories: as local coupling and distant coupling, and also known as multipath propagation. In local coupling, the most common type of crosstalk is caused by coupling in closely routed signal traces. I'll use examples today only from this illustrating this type of crosstalk because of its well, it's the most important. But our tutorial at DesignCon was covering also some other types of like local coupling between vias and vehicles and traces, coupling of traces through cutouts, common to differential conversion, which is also maybe considered as a type of crosstalk. Distant coupling and multipath propagation is a phenomenon that is much more difficult to simulate and to account for. So it's coupling through parallel planes or PDNs, through splits planes, through surface dielectric layers, through PCB enclosure, and through the environment in general. So they some of them are internal to PCB, some of them may be external. So it's EMC, EMI, so-called issues. I'll talk about quantification here, and the methods of quantification: frequency, time, and probabilistic domains are applicable to all types of crosstalk, actually. But to start with, we need to understand how the signal propagates in the interconnect. So to illustrate it, I use power flow density here. Alternatively, we can use electric field values. So as we can see that electric field is in the air. This is signal trace between those are reference planes here. Same with magnetic fields, and vector product of electric and magnetic field expressed in dB right here is a power flow density. So essentially, it's where power of your signal propagates in space between those metal structures. So that's why I call those in general PCB and packaging interconnects as open waveguiding structures. It's not enclosed on two sides at least. So and this is stack up details and so on, how it was computed. And those examples also can be downloaded from our website. And you can play with, see how things happen, how interconnects work. So this is illustration of differential case, and this is unsymmetrical strip line. If you start moving, usually assume that all the currents are going through the closest plane, and that energy is localized somewhere here. It is partially true. So you can see that this red area here, where most of the energy propagates, is quite localized. But then you see this green area with level of power -30, -45, and blue is -60 actually, where it spreads even beyond this area here, and the scale here is in mils. So it's quite wide area, and anything that gets into this area is coupled for sure, and may potentially have crosstalk. Things even worse for microstrip structure. This is surface trace on the surface of PCB in layer signal 1. Those are parameters of this, and we can see right here two graphs overlap actually. One graph is power flow density color plot, and electric field is depicted in on logarithmic scale with arrows of the and those arrows do not really go through the metal, so it's just kind of the origin show where they're located. They are just quite long, and you can see the value, the length of the arrow correspond to the value. So they are not punching through the reference plane. So what is the problem? The problem is that we have a large area here, and this is just below minus 60 dB that is potentially coupled. For digital interconnects, minus 60 may be not a problem, but for RF microwave structures, that may be a problem even beyond this. Again, if you switch to differential, we can see pretty much the same picture. So it usually assumes that differential has more localization. Yes, we have more localization in this area, in the area of air, below the traces, but we can also see that the field spread in the air. To illustrate how it happens in 3D, I use this recent example generated for a conversation with Robert Feranik, and the recordings of those conversations on fields. Robert suggested a few configurations to analyze and see the fields and currents in there, and this is one of them. This is differential microstrip structure, like 16 mil traces, 16 mil separation on 8 mil substrate, typical FR4, and we can see power flow density here right below the traces. It's in color, and we can see higher power flow right below the traces. Then we can see the same thing in form of arrows and volume, and one cross section here shows where the fields are spreading. So the signal at 16 gigahertz propagate from this end to this end, and we can see how it migrates into the adjacent differential pair, which is just one W spaced here, very tight coupling. And why it is, we can take a look at another cross sections, like right above the traces. So we can see that field or power flow or signal space, I call it signal space, is spread in this case and goes over the victim. And we can see on this end fine crosstalk, on this end near crosstalk, and this is even above, more above the traces. In the air, we can still see a lot of signal propagates through in wide area. So same at 28 gigahertz, and this is in 3D. So we can see that one common way to deal with this is to increase the separation. But in case with microstrip, it doesn't work really well. So right here, it's separation, 3W, 4W probably. And we still see the signal getting into the victim, both on near end and most of it on the far end. So we can see how it gradually gets into the fine crosstalk. And same thing. This is because of we got signal space very wide in the air in this case. Even if we don't have it much intersection of the power flow with the neighbor victim, so we still have a lot of energy basically overlapping with this in the air. So this is even above. So that's how it looks like. And on the same scale, you can see how signal propagates. What is the signal space? Okay. This is it on crosstalk anatomy, and more you can see it in this presentation, and also at those recording of conversation with Robert Ferrani. Those are long and with explanation of details of what's going on. So considering the quantification, I put 4 approaches here. One is with a coupling coefficient, very common, covered in all books and a lot of papers using this. That's usable for preliminary estimation. And technically, it belongs to time domain, approximate way to do the time domain evaluation of crosstalk. It's analysis of possible crosstalk with unit voltage excitation. Frequency domain is the main way to characterize crosstalk. It's based on scattering parameters. I'll talk about this more. Time domain, it's simulation with step, pulse, or pseudo-random bit stream. And relatively new in signal integrity, probabilistic domain. It's statistical evaluation of crosstalk on channel operating margin. And I'll talk about it as well. So to illustrate all the quantification methods, I will use Crosstalk 2832 validation platform from Wild River Technology. So they provided all the details for the design and as well as measured data. Actually, interesting story, the prototype of this platform, Simbeor 08, was used in our 2011 design con paper with a lot of people collaborated on validation of analysis with measurements with validation, and so on. The purpose of this platform is sometimes misunderstood. So it's not just to see the analysis to measurement correlation, but actually to practice this systematic approach that we use with our customers for a long time already. It's called Sync-O-Swim approach, and there are a couple of webinars on this, including some platforms from Wild River and application notes as well. So it's a systematic approach where you do certain steps, like identify material properties on the basis of a couple of transmission lines. It includes dielectric and conductor roughness models. And then identify adjustment during the manufacturing with a cross-section. And then apply it to analysis of all other structures without any adjustments of the properties of the parameters of the analysis. And that's important. And that's how you know how predictable your simulation. And obviously, those platforms allow you to measure practice measurements, which is also difficult if you think about 50 gigahertz or even now 70 and higher gigahertz. So crosstalk evaluation with coupling coefficients. I put those 2 formulas from Eric Bracken paper here. The original formula was from Jarvis paper, but Eric Bracken modification includes this maximal values here and allows to basically shows you that that's why crosstalk is near and crosstalk is this right here. It's a backward coupling coefficient is getting maxima when rise time is when the electrical length of a line is half of rise time. So it's basically magnetic and capacitive and inductive coupling define those backward and forward coupling coefficients. It doesn't account reflection, losses, and so it can be used only as a first step to evaluate the possible value of crosstalk. And right here, important note that peak-to-peak crosstalk maybe exceeds this value 2 times by 6 dB. So to illustrate how to apply this formula, I use Simbeor SDK, which is really wrapper around all Simbeor solvers and tools, and it includes this advanced crosstalk kit where you can quickly enter the geometry and evaluate the value of crosstalk with any method, actually, not just with coefficient, as I illustrate here. It inspired by this talk by Scott McMorrow from Samtech. So I use cross sections about the same as in that presentation. So what can you do with this? You can create solution spaces, evaluate where your crosstalk essentially satisfy your requirements. In this case, it's minus 72 dB, for instance, strip lines. Distance between traces is defined by the impedance of the differential impedance, and then we use pitch, change pitch of between the differential pairs, and we can see that the crosstalk goes down. And if distance between traces is smaller, then crosstalk is smaller. It drops quicker. And this is just linear scale. On linear scale, it's not so kind of obvious how it behaves. This is fine crosstalk or forward coupling coefficient. You can see the behavior is a little bit more complex with microstrip line. So you can see even minima of the defined by the soda mask. You can adjust actually soda mask parameters to have very low fine crosstalk, but it's purely theoretical. So in reality, manufacturing with such precision is well, practically impossible because of soda mask doesn't have any kind of precision when it is applied. So, but you can see that the smallest crosstalk is happen at shorter lines and at longer rise time. So this formula basically it relates this length, rise time, and so on. You can experiment with this and see how it. Rather than remembering what it is, you can directly do in computer. So with near crosstalk, if we have too short segment or longer rise time, we can see that it's smaller, but then it saturates. So that's what is important to know about near and fine crosstalk, how it happens, why it happens. There is my take in this tutorial. You can look at those slides and see explanation, or rather kind of, it's not explanation, it's observations, I would say. Okay. The approximate analysis of crosstalk, where it comes from, can be used in post layout as well. And I can demonstrate it with how to do this in Simbeor software. And this is Crosstalk 28 board. Before the analysis, I adjusted the bit rate rise time here. Those are the most important parameters for crosstalk evaluation. And I will use electrical rule checking mode, where I will evaluate reference integrity, impedance continuity, and crosstalk noise. So instead of dozens of geometrical rules in Simbeor, we use rule checking based strictly on electrical properties. So the older specifications, they may tell how many widths you have between you have to have between traces to have certain crosstalk, but it's better to express it directly in electrical properties. So before the analysis, I use extract reference conductors to select all the links here and simply click run. So it will collect about a few hundred cross sections, evaluate parameters of VS in there. For right here, it's about 15, probably 15 structures. And I adjusted the view to see crosstalk only. So, and in addition, we see impedance also, and we see problems with reference integrity shown here. So it coincides with basically very high crosstalk, very high impedance, so the reference is violated. In all other locations, references are not violated, and we can see signal conductor as well as the reference conductor. We see those waveguiding structures here. So, but returning to crosstalk, you can see that crosstalk some locations like 69 millivolt. This is just one width separation here between the traces. And you can see that crosstalk also affects the impedance. So the impedance, despite the same distance, impedance is going up and down a little bit. So, and then there are a few more structures, same three differential links, but with 2 widths, 3, 4, and 5 width separation. And there are other structures with just 2 differential pairs coupled. So we can see that crosstalk is going down as we separate the traces, but it's still substantial in even with 5 width separation here. So and this is done just for preliminary evaluation to see local sources of the crosstalk. All the parameters of other parameters on this crosstalk 28 board are shown here. And also for the analysis, actually, there was some adjustment of geometries right here defined because of the board is when it is manufactured, the geometry is slightly different from what you get in your design. So that's those adjustments are important if you have if you need to see actual impedance or even actual crosstalk. So small variation width may give you large variation in crosstalk, and that's important to have it. So frequency domain. This is where everything interesting happens. So the digital signals are a sequence of pulses, modulated pulses. It's time domain technically signal, but and everything that happens with the signal, absorption, dispersion, reflection, coupling, and radiation, it's the best way to simulate it is in frequency domain. In the frequency domain is a harmonic solution of Maxwell's equation. Basically, this is the math behind it. So when we talk about frequency, we talk about sinusoidal signal and all the effect, all the degradation factors, they are frequency dependent, and those words. And then when we obtain the frequency response of links, then all other types of analysis can be done with this response. But to start with this analysis, we have to know what is the bandwidth in frequency domain. So, and the bandwidth right here to illustrate how the bandwidth can be defined. I use power spectral density of a signal, 112 gigabit PAM4 for picosecond rise time, with all other parameters shown here. And you can see that the original spectrum blue may be really kind of white. Even if you take it -20, you can get all the way up to 100 gigahertz in spectrum. But fortunately, when it gets through interconnect, even relatively short interconnects, it's filtered. Interconnects, they work as low-pass filters. And this brown spectrum is a signal that gets through 10-inch strip. So for analysis of insertion loss and fixed, we can restrict our bandwidth to just 2-3 Nyquist frequency. Nyquist frequencies here is 28 gigahertz. So, for the next, you cannot do this. You have to do either analysis up to the highest frequency that may degrade may cause the next, or you have to avoid it with other means, isolation and localization. So this is how the bandwidth of analysis looks like for different signaling data rate. And the data rates now getting into 448 even. And some companies already reported that they can transmit PAM4 over substantial distance. But the Nyquist frequency for this 448 PAM4 is 112 gigahertz, and you have to simulate it up to, or measure to up to very high frequencies. I haven't seen such measurements, so theoretically we can simulate it, but measurements and correlation will be difficult. But down to earth, to more common cases, you can see pretty much everything above 10 gigahertz NRZ is in microwave and then in millimeter wave frequency domain. So that's scary part, and that's why you have to have serious equipment, serious solvers to handle this. And in frequency domain, we use S scattering parameters. And if you on Simberian websites, there are tutorials. My first tutorial was on scattering parameters at DesignCon, probably like 15 years ago. And back then it was new to signal integrity, relatively new. Right now it's a mainstream tool. And right here you can see Wild River technology measurement setup with the measured results taken by LNAVs. And analysis in Simbeor of the same structure, phi and crosstalk. So first think that you do when you do analysis to measurement correlation, you probably do the analysis of scattering parameters and do compare it, or set up the limits on those. So this is the most obvious thing to evaluate the crosstalk. So and in form of S parameters, if it goes down, then the smaller the value in dB, the smaller the value in volts is going to be. How it correlates with this, we'll see. Additional steps are needed. So right here I show only magnitude of scattering parameters. There are also phase, delays, and so on, so that defines the behavior of signal in time domain. So power sum crosstalk is a way to express crosstalk from multiple aggressors in one number. Very convenient to set up the limit for this. It's right here. It's simple sum of squares of S parameters expressed in dB. Again, it may be near crosstalk, fine crosstalk, and so on. This is just for convenience. In case if there is just one aggressor for facts and x, power sum crosstalk coincide with the original S parameter. So it's kind of things that you have to know. But as long as there are multiple aggressors, then power sum crosstalk is this sum of squares, and it accounts only for magnitudes, not for phase. So the phase make difference actually. But to illustrate how it works, I use 3D EM analysis in Simbeor. And all I need is just to switch 3DSI and define the corresponding metrics here. So I want to compute magnitude of crosstalk as parameters, and I want to compute power sum crosstalk. And click run 3DS analysis. So Simbeor constructs used decompositional electromagnetic analysis. It builds 3D EM models only for those discontinuities and reuse it all over this place. So all those are identical. So Simbeor reuses them. I pre-computed them. I should say that to avoid a couple of minutes wait. And everything was pre-computed here with high accuracy, so that's sufficient for correlation on this particular board. So the result we can see in form of mini plots, and right here there are on transmitter side we see just return loss and TDR, and on receiver side we see all other parameters, including those we requested from Simbeor. And the most affected link is this one. So we can see this is the original crosstalk scattering parameters, and power sum crosstalk is actually sum of these squares of those. We can see that phi and crosstalk is smooth here, but then power sum crosstalk contains this spike from near crosstalk. So as simple as that. So same for larger separation between the traces. So we can see that the crosstalk goes down and power sum crosstalk goes down as well. So insertion loss to crosstalk ratio, another metric that is useful. And the reason for this is if you have if your link has smaller losses, it can tolerate more crosstalk. And this is simply difference between insertion loss and power sum crosstalk, as simple as this, but it can be interpreted as a signal to noise ratio. So power sum crosstalk, original power sum crosstalk is negative, so with plus it basically when it goes down it's smaller crosstalk, but in this metric it pushes it up. So the higher the metric, the lower the crosstalk and better the structure. So okay, I can demonstrate it on this link right here, pathological structure, where there is a short link and there is a long link. I selected the link, and again I run 3DSI analysis, and it will collect all those, build all those discontinuities, and which looks like this. This is, for instance, launch, coaxial launch de-embedded to this position. And in the analysis, there are also connectors actually included in the analysis in this section over here. So we have connector model here, component port in form of coaxial, and so on. And this is and everything is done automatically in Simbeor. So and this is result of analysis, and we can take a look at the okay, I didn't check this metric. and this is ICR. ICR, and right now it will not run, it will just collect those metrics, and that's it. The ICR for shorter link, you can see it goes a little below 30 dB, but if we get for longer link with more insertion loss pushes it down, so you can see it goes below 20, and then it even goes below 0. So, okay. This is illustrated on a slide as well with some explanations, and next metric is using contemporary specifications for links is integrated crosstalk noise, and Power-sum crosstalk, S parameters, and ICR are frequency dependent. You have to put some mask on it. But this is just one number, and this number is obtained with is the next of X, summed with some weight, and weight include filtering and signal spectrum. This is one number that is easy to understand, and there is more. If you need to read more, you can see this Shimanuchi paper, and with the details, or in some standard documentation. It usually plotted as insertion loss voltage value versus insertion loss, and mask may look like this. So it's the higher insertion loss, you must have smaller ICN. So that's basically the physics of this. So crosstalk and time domain, I'm getting very quickly out of time. So you have to measure crosstalk. You can measure crosstalk directly in time domain as maximal peak-to-peak value of voltage response. It can be done with more realistic model, but analysis of such analysis have some uncertainties. So, what is the aggressor? What is the timing of aggressor, and so on. That's not definite answer what amount of crosstalk you will encounter. So comparing the fine crosstalk, for instance, O'Neill crosstalk from step response and pulse response, you can also notice that the value of crosstalk may be as different as 2 times. So peak to peak, or just one way. This is example of how to evaluate X and X without, not with approximate numbers, but with direct computation in time domain. Example of such analysis, again, it can be done with one click in Simbeor. You just select in SI compliance analyzer what type of crosstalk analysis you need, then you run it, and then you see the values in those mini plots, and then you can construct reports which value exceeds this specified value. Same with PRBS response. You can combine, you can compute as a I diagram directly, or I diagram that includes crosstalk. So I'll demonstrate it in a moment. So you increase spacing by 4W in this case, crosstalk drops in time domain, and effect of crosstalk on I diagram also drops. So, and the uncertainty illustrated by this slide. So you have original I, and then you put some neon crosstalk and fan crosstalk on it. But timing is uncertain. You get I shrink in both directions. You have more jitter, and you can more amplitude noise. So why it is uncertain? Because of the original bits in all 3 channels are not correlated in time, so they are not starting at the same time. They are kind of randomly transmitted, and you have this noise randomly distributed around one victim, this red link. So, and they can appear as a jitter or as amplitude noise. So if you switch to probability, and this is the last kind of way to evaluate crosstalk in probabilistic domain. So, and you plot probability of fine crosstalk, it will look like this, with 3 or 5 peaks in there. And near crosstalk will look more like Gaussian distribution. And then if you put like 4W, the amount of crosstalk decreases, and this is a probability density. So it basically characterize probability of crosstalk happening at this value or at this value. And near crosstalk becomes more Gaussian, and fine crosstalk still kind of more complicated. So to account for this probabilistic values, there is a metric, channel operating margin, that is basically signal to noise ratio, a kind of where signal, you can look in documentation how signal defined, how noise defined in there. But the noise includes probability distribution of the crosstalk if you include the S parameters of aggressor links. So computation of COM requires S parameters of the original link, and then S parameters of the all aggressors. And you can see more in those papers reference here. But the bottom line, you can basically supply COM script with S parameters of the aggressors near and define crosstalk, and COM will take those into account as probabilistic measures. It overestimate overall. So we on those structures we can see that the still open eye, but the COM because of a lot of crosstalk may close the eye actually on COM for specific bit error rate on. So and let me do the last demo, and I switch to this link and want to compute eye diagram and eye diagram with crosstalk, maybe crosstalk from pulse response. And all I did is just select corresponding metric and click run. And this is reuse of the same 3D analysis. In a moment, the eye diagram computation takes a little bit longer, and we'll see the resulting eye diagram. Not channel operating margin yet. This is coming in 2020 version 2025. But right here, if you take this victim that has near and defined aggressor, so we can see that the pulse crosstalk is looks like this. This is with default 1 volt excitation, peak to peak. So the excitation may be further adjusted if necessary, but this is 1 volt again spread of the signal with this is original eye, and this is eye with crosstalk. You can see that it's considerably looks considerably different. So if we do want the same type of analysis with any other separation, like 4-bit separation, for instance, I switch and select this 10, 11, 12. This link, all I need is just to run the analysis. It will run the analysis and again reuse as parameters of all discontinuities and build the model for transmission line coupled in the middle, and then collect the analysis is done and collect the same measurements specified. That setup can be saved as preset, loaded with the metric, masks specified in form of polylines, of formulas, and so on. This, you can learn more at Simberian website. So, in conclusion, I should say that there are multiple methods to evaluate and model crosstalk, and each of it has some value. So, in and the analysis basically done. So we can see, sorry for switching this to this. We can see the I diagram now original in I diagram with a crosstalk. They're practically identical. So like that, practically identical. So the I diagram is the ultimate metric of how crosstalk influence signal propagation. But all the other metrics are important. So for troubleshooting, for setting some limits on this equation base is probably the most limited one way to evaluate crosstalk and time domain. But frequency domain as parameters and multiport theory in general, those are the basic for all other types of analysis, no matter what is probabilistic or time domain, they're all based on this one. So technically, when you troubleshoot, you get back to S parameters and so on and see where it happens and so and frequency, time, and probabilistic domain metrics are useful actually for all type of crosstalk, not only between traces as I demonstrated, but for via crosstalk, for anything else. So now we have some time for questions, and I have just one question. Okay. Can we build this simulation on HFSS? Of course you can. Can we build these simulations on HFSS? Of course you can do it. I don't know how easy it is or how it is done, but right here it was live. The only thing I prepared, I just run analysis of the discontinuities extracted from this geometry, and then again extraction of the discontinuities. And assignment of all types of ports, and it was automatic. So that's all this geometries was automatically extracted and simulated in frequency domain, ports attached, de-embedded, and so on, then reconnected in the final link. And okay, we got more questions here. There are so many standards to evaluate crosstalk, such as ICN, ICR, COM. Which one is suitable for analysis in time domain, frequency domain? So ICN and ICR are based on basically frequency domain response. So it's frequency domain response. ICR, it's a ratio of insertion loss or to power some crosstalk. ICN is a frequency domain response converted into time domain with taking into account more realistic, spectrum and more realistic behavior of transmitter and receiver, so filtering properties. COM is purely based on frequency domain. So S parameters, those S parameters that you supply. Those are kind of final metrics that are all based on S parameters. So any more questions? And, can we use full PCB to analyze? Yes, sure. You can use full PCB. What is more realistic way? Yes, you can do this instead of 3D analysis. Yes, 3D decomposition analysis that I used, where Simbeor finds the discontinuities and treat everything else traces as transmission lines. And right here, you can see those transmission lines. I didn't use more realistic PCB because of this is demonstration and of how things work first. You can see more realistic boards on our website, analysis of crosstalk and VS and crosstalk Another way to analyze it is to put everything in 3D EM analysis. You need much more powerful computer. It will take much more time, and the result is not guaranteed to be more accurate. So such analysis will include definitely other effects like interaction with the external waves coming here and radiation. But the goal of design of interconnect is to make it localized, so not radiating, not interacting with other. As soon as you follow those goals, the structure becomes more and more accurately simulated with the decompositional analysis. So it coincides with the design goal. And basically, you converge to proper design. You satisfy all those localization properties, and it becomes simulatable in isolation. And this is kind of mutually or alternative, you simulate the whole thing or the whole board. Some people simulate even the whole board. Take a long time, but then take a look at the TDR, for instance, or at the crosstalk evaluated with such analysis, and use crosstalk 32 board to correlate, or CMP70 actually. We recently get CMP70 from Wild River Technology, and just visit their website. You can see plenty of the boards for the analysis to measurement correlation, for repeating the process of how predictable are the interconnects, and how and they all very localized here at CMP70 up to 60 gigahertz actually. Right here it's up to 45, I believe. Okay, is power some crosstalk in dB or dB voltmeter? It's dB, just dB, no dBm, no dB voltmeter. How about non-uniform microstrip line? Is it possible to analyze? Yes, if you take a closer look, the microstrip lines here, the width of them is changing. It's clearly visible on impedance profile. You can see that the traces are becoming narrow, narrow, narrow. So the transmission line approach works. But you can alternatively put a discontinuity selector around and do the analysis as well. This is not automatic manual, but as easy as any other analysis in Simbeor. So in this demo file with multiple design cases available to download and play with different parameters. Yeah, absolutely. Yeah, we can. The Simbeor solution file is available. I can just ping me. I can send you the link on Google Drive, and there you can play with this and well, buy the word, measure it, and well, correlate it with the measurements and see how it works. So, more questions?
Okay, it seems like we no longer have any questions. Thank you very much, Yuriy, for presenting, and thank you everyone for attending. I will send the slides and recording this afternoon.
Thank you, Lucy, for organizing it, and thank you everyone for attending, and just well, go to Simberian website and download and try Simbeor today, and on your design, or see how it works. Thank you.
Thank you. Have a great day, everyone. Bye-bye.
Goodbye.